Well, thank you everyone for joining here. So yeah, I wanted to talk about the space weather modeling topic and especially the use of AI in space weather, which is, I mean, it's not recent, but it's starting to have really nice results and starting to use AI broadly in the space weather community. So I wanted to present a bit this. I'm more of a space person, so maybe some of you, most of you, might know much more in AI than I do. But I'll try to introduce both topics, and mainly space weather actually. So yeah, thank you, and thank you, Patrick, for letting me do this presentation. Do not hesitate to interrupt me if something is really not clear, or if there is any issue in I don't know, the mic or something. And I think we have a Q&A at the end of the session, if I'm correct. So yeah, I'll just dive in. So I wanted to talk about the space weather impacts on so space weather, which is like a theoretical a concept with a lot of person working on, and how space weather impacts the space assets. So, and also on ground actually technologies, and then talk about how the artificial intelligence arrived in this community and how it is used today to try to predict, to forecast a few things in space weather. So yeah, first I will introduce myself because Patrick asked me to do it and present some of my background. Then I'll try to do an introduction to space weather, which will not be very technical. It's just like a general introduction. Then I'll talk about nowcasting and forecasting space weather. So some obstacles and challenges in modeling actually space weather, and why AI appeared. And then I'll try to give some examples of how we applied AI to space weather. I'm actually staying a bit general on the different examples of AI applied to space weather, but this will be the occasion of discussion after the presentation. And finally, I'll talk about one example, and this example is actually my PhD thesis. So I'm defending my PhD in October, so most of the results are there already, and I'll try to give you an overview of the different difficulties and how I try to solve the issue that I'm working on. So first, a quick background of my background and education. So I'm an engineer, French engineer from the ISAE Superior. I did a Master of Science in Aeronautics and Aerospace, and I specialized mostly in actually astrophysics and space sciences and design of space assets and space operations. I did a double degree at the end of my studies with a Master of Research in Astrophysics, Space Science and Planetology, and I had the opportunity to do the final internship of my studies at NASA at the Goddard Space Flight Center. I was a research assistant at the Cosmology Lab. And right after this experience, I ended up at SpaceAble, which is a startup. I might have a few words about SpaceAble at the end of the presentation, but basically I'm a space weather analyst and data scientist, so I'm not really an engineer, but I'm working on space weather problematics at SpaceAble. So I'll talk about SpaceAble maybe later. And I started in October 2020. I started a PhD in applying artificial intelligence to space weather, and I'll get back to it, but it's actually applying machine learning to try to forecast specific electron fluxes in low Earth orbit, but I'll come back to it.
And Simon, One question is now you're doing artificial intelligence for space weather. In your background, where did it started? Where did you started to get your hands into data analytics specifically? Was it with your PhD or prior to that?
Yeah, it's actually directly in my PhD. I mean, it was a bit prior, but during my job at SpaceAble. So my background during my engineering master was not really focused on artificial intelligence, although I did a lot of coding, so I was used to code, but I didn't really know the different problematics and how artificial intelligence is working. I mean, that's why I'm a space person and not, not an AI person, but I had to get my hands on it for the PhD. And I'm using artificial intelligence as a tool. But my major in my PhD is mainly astrophysics. So AI is really for me a tool. But it's actually really interesting. So I'm glad I started artificial intelligence during the PhD.
All right. Okay.
Okay, so about space weather. So space weather, the main definition that we can find on the internet is based on NOAA. So NOAA is the American National Weather Institute. So all type of weather, but also space weather actually. And so space weather, they define it as the conditions on the sun and in the space environment that can influence the performance and reliability of space-based and ground-based technological systems, as well as endanger life or health. So it includes phenomena like solar flares, geomagnetic storms, cosmic rays. I don't know if you heard about it. I'll try to explain some of them in the next slides. And understanding space weather is really important for ensuring the safety and reliability of our technological systems, and especially the technological systems that rely on space-based assets. So space weather is just like weather on Earth. It has seasons based on the solar activity, and it's folding over an approximate 11-year cycle. So I'll come back on the different data that we actually use to measure this solar cycle or to represent what's happening in the space weather in general. But one of the main measurements used to identify this 11-year cycle is the number of sunspots that we can find on the solar surface. So you have here a picture of the sunspots, and on the left you have the graph of the measurements that have been made. So the sunspots measurements that have been made since 1950. So we can really see this 11-year cycle, but we can also see that these cycles are not really different from one another, and some of them are really less eruptive and less violent than some others. So there are a lot of phenomena in space weather actually, and I'm not going to present them all, but just trying to give a quick review. So I'll start by, so I'll do like the sun to Earth chain. So I'll try to start from the sun and then go straight to the Earth and try to present the key locations and the key events and phenomena. So to begin, we focus on our closest star, so the sun. So the sun is a massive sphere of hot gas and plasma, and it's constantly in motion. So it has the 11-year cycle that we mentioned, and it also has a 27 days rotation period. And actually the rotation is not uniform on the surface of the sun. It is quicker at the equator and slower at the pole. we can observe a lot of things on the sun. We can observe dark sunspots on its surface. Sunspots, as I said, are a sign of the intense magnetic activity in a local area. We can also observe coronal holes. So coronal holes, you have one on the right side picture. These coronal holes are often places where a lot of particles are emitted from the sun. The sun also, in these active regions, generate powerful solar flares, for instance, and coronal mass ejections. So coronal mass ejections, here I've written CMEs. We usually just use CMEs to talk about it. It's an incredibly massive, like billions of tons of matter that are hurled into space at very, very high speeds, sometimes up to 3,000 kilometers per second. And so it usually take 1 to 3, 4 days to arrive on Earth. So when you have a huge CME, you will have a huge impact on Earth. Usually, I mean, if the CME is directed toward Earth, but you have 1 to 3 days to prepare for the impact. And although CMEs are often associated with solar flares, they can actually occur independently. And solar flares, I mean, when we talk about solar flares, we're talking about massive explosions on the surface of the sun. And it's a lot of energy, but this energy is usually in the form of radio waves, so sometimes visible light, ultraviolet radiation, radio waves, X-rays, and actually we observe, we make some X-rays, fluxes measurements. There is satellites from NASA, which is called GOES, a satellite that it is in the geostationary orbit, and this satellite is measuring the X-ray flux. So it's almost not instantaneous, but it's a few minutes from the solar flares to the Earth as it travels at the speed of light. And there is also the solar wind. So the sun is actually emitting a lot of particles all the time. So when we start to get far away from the sun and we arrive in the interplanetary medium, what remains mainly is the solar wind. The solar wind is a constant stream of particles, so mainly electrons, protons, and sometimes heavier particles, alpha particles, that are released from the upper atmosphere of the sun. And within this flow of particles, there is something called the interplanetary magnetic field. So you can think of the magnetic field. So the magnetic field of the sun is really chaotic. If I come back to these pictures here, so just the small videos is coronal mass ejections, and the picture below is an artistic representation of the magnetic field of the sun. So it's really not a classic dipole with a north and south pole like on Earth. It's really chaotic magnetic field, and it's very, very difficult to model. And so this magnetic field release particles, and the particles and the magnetic fields are said to be so the particles are said to be frozen in the magnetic field, and it's just to say that particles and magnetic fields are moving together in a direction. And it's so we have this huge interplanetary magnetic field that has the shape of a spiral. It's actually the Parker spiral. We can see it on the right side of the screen. And this magnetic field has a significant impact on Earth, on the Earth's magnetic field, and it is shaped by the pressure actually of the solar wind, and this magnetic field will collide with the magnetic field of the Earth. And the solar wind is also, of course, characterized by its speed, its temperature, its dynamic pressure, and so on. And we have a lot of satellites. For those who know the Lagrange point. We have a lot of satellites, especially in the Lagrange 1 point in the interplanetary medium, to measure the solar wind that is arriving to on Earth, and is a good indicator on the dangers. And it's worth noting that the coronal mass ejections are also affected by the solar wind, and they travel through space, and they are slowed down by the effect of pushing through the wind. And usually the fastest CMEs that we see that arrives on Earth are usually the result of several CMEs that combine, with sometimes the second one propagating behind the first one, actually. So this is just to say that there are a lot of really interesting and difficult and complex phenomena that are happening on the sun, and the sun is also very, very difficult to understand. A lot of things are still unknown on how the magnetic field is working. And also in the interplanetary medium, even though we often think of space as being empty, it's not at all, and it's very, very complex to make measurements there. And then we arrive on Earth. So on Earth we have our magnetosphere, and so our magnetosphere is mainly, so for maybe some of you knows this, but our magnetosphere is created by the rotations of the metallic fluids in the core in Earth's core. And this magnetosphere actually protects us from all the particles and the radiations that are sent from the sun. So to give maybe a quick rundown of the different zones of the magnetosphere. So we have the outermost magnetosheath. We can see it next to the shock front. So the magnetosheath is the outermost region of the magnetosphere, where it's really where the Earth's magnetic field interacts with the solar wind. Then we have the shock front, which is the boundary between the solar wind and Earth's magnetic field, and the first point to touch the solar wind. And we have also the innermost region, so like the plasma sheet, for instance, the Van Allen radiation belts. So the radiation belts are like two donut-shaped regions of high energy particles that are trapped by the Earth's magnetic field. But I won't go into too much detail. It's interesting to notice that when the solar activity is really high, the magnetosphere in the front is compressed by the effect of the arriving solar wind, and it's something like 70,000 kilometers from the center of the Earth, which is not really that much. And on the other side, the effect of the solar wind is actually extending the end of the magnetosphere like a tail, and we often talk about the magnetotail. And this is millions of kilometers on the night side, so it's really not symmetric at all. It's a huge, like a comet-shaped magnetosphere. So this gives you a glimpse of the space weather context, but what interests us when we work on space weather, especially when, like me, we're working in the industry too, are the potential impact and how all of this is actually impacting on Earth and in space our technological assets. So I don't know if it's written, it's big enough, the font, but this is a nice slide from ESA, where we can see a lot of different impacts of the space weather on the different aspects of our space technologies. So mainly, what we distinguish when we are working on space weather, we often distinguish the sources. So the sources can be the solar protons, for instance, or the coronal mass ejections, or for instance the plasmas, the magnetic field, and so on. And then we talk about the mechanisms. So the mechanisms is what is actually triggered by the sources. So sometimes we have single event effects. I don't know if you heard about it. So a single event effect is when a single really high energy particle is actually impacting something like a satellite or a power grid. And this single particle can, for instance, change the code inside your satellite, or can just destroy one cell of your solar panel. And it's very, very, very difficult to predict and prevent this type of impact, because the single particle, even if they are really high in energy, are impossible to track. A single particle is impossible to track. So what we can track is coronal mass ejections or solar flares. So we know when a bigger amount of these particles is about to arrive on Earth, but we don't really know if one particle will impact this component in this satellite and then destroy the satellite. And so this is single event effect. We have also the total dose, for instance. So it's mainly radiation on satellites. The surface charging, for instance. So surface charging is when you have charged particles, mainly electrons, that are accumulating on the surface of your satellites. And sometimes, so it's a bit simplified, but sometimes you have difference of potential at different point of your satellite, and you have electrical discharge that then happens and totally destroy your batteries and components. And we have also internal charging, so the same effects can also happen inside the satellite. And from this, there are a lot of. I can maybe I'll try to go by some actual events that occurred in the past. Of course, I chose the most impressive ones, but they are pretty rare actually. So the most known event is the Carrington event that happened in 1959. It was a series of solar flares that took place during the summer, and it's considered to be the most violent solar storm to ever hit Earth. For instance, the polar auroras are actually a good indicator of the impact of the geomagnetic storm. So when you have a big geomagnetic storm, the auroras are starting to go down in latitude. So you can start to see them even in the north of France or the south of England, for instance. And this happened actually not that long time ago. I think a few weeks ago, we had a big geomagnetic storm, and the auroras actually went down at low latitudes. But for the Carrington event, we were able to see auroras as low as Mexico. So it was really it was actually the biggest, the most violent storm to ever hit us, and it had a lot of violent consequences. But in that time, and we didn't have any huge electrical or technical systems, so it wasn't really that problematic. However, in 1989, there was a major eruption of the solar cycle 22, and it's, so when we say major eruption, is something like maybe 10 times lower than the Carrington event, but still a big eruption. And it ended up in the collapsing of the whole Quebec power grid system for 9 hours. So 5 million people were into darkness for 9 hours. And in 2003, we had the Halloween storm. So it was actually a quite violent storm. We are still studying it because we had a lot of satellites back then. But 28 satellites were damaged. And when we say damaged, we lost 28 satellites. And there were a lot of disruption in the Sweden's electricity distribution system. And of course, all the following consequences, and I'll come back to the consequences, but sometimes errors in the GPS and so on. And in 2012, there was a solar superstorm that missed Earth, but was not really that far from Earth, and the consequences were estimated at $2 trillion. And NASA mentioned it as a solar storm that could have sent civilization back to the 18th century. Of course, it's, I think, a mediatic interpretation of what they said, but it's in fact a very violent superstorm. There are some papers that are trying to link failures and incidents on satellites to space weather, because space weather is really well studied in its community, but the link to operation and failures on satellite is not studied a lot. There's not that much people that are working on this. So there is a study by Tafazoli in 2009 that estimated that 17% of failures are related to space weather, and that it represents several billions or $1 million, depending on the countries, as a consequence. And since the beginning of satellites, actually, we lost 1,600 satellites due to space weather, which seems to be not very much, but we are sending a lot more satellites today than we used to, and this number is for sure about to increase a lot.
Simon, is it so? Is it just the location? So we lost where they are, or is it really we know the satellite have died after this failure?
Both, actually. So some of these satellites are lost because they are actually, this is one consequence, because they are actually changing orbit a lot. Because when you have a lot of solar activity, the ultraviolet radiation from the sun is actually heating up the high thermosphere of the Earth, and when you hit it, it starts to expand, and so you have very dense portion of the atmosphere that are going up, and satellites that were not supposed to experience drag on molecules are actually having a lot of drag because the density of the thermosphere is increasing for them. So actually some satellites are changing orbits by a pretty big amount, and these changes in orbit sometimes make the mission control lose satellites, because you don't really look at your satellites 24/7. So sometimes you have a large amount of time when you cannot see your satellite, and you expect it to come back at a certain point, and sometimes it does not come back because of this. In the 1,600 satellites that I was mentioning that were lost, most of them were then found again at the end, but this gap of time where you don't know where your satellite is are really problematic with the collision risk, and it's going to be even more dangerous in LEO and with all the constellations, for instance from Starlink or others, and if you lose satellites for a large amount of time, you increase by a lot the risk of collision, because you cannot really warn everyone that your satellite is on the path of another one. Yeah, I mean, basically space weather has always been an issue for satellites, but the first satellites were tested with a large amount of shielding and protections against radiations by NASA and everyone. So So most of the first satellites are pretty much safe because they based their studies on several years of solar activities. The real risk arrives when we start launching satellites that are very small with less redundant technologies, like less batteries or less shield and so on. And most of the satellites that are sent today are sent like the new space generation. Most of these satellites are not protected enough for space weather. Even more because the past years have been really low for solar activity, and we expect solar activity to increase by a lot in the upcoming years. And most of the satellites today are not really ready for what's about to happen in the solar activity. Does that answer your question?
Yeah. Thanks very much. It's really, I haven't thought that. Yes, indeed. Now with the new space weather is becoming even more important because of the factor that you mentioned, less redundant equipment, low cost. So it's a very good insight.
Yeah.
Good takeaway.
Well, last year, for instance, SpaceX sent several satellites. I think it was in February, and they lost almost all their satellites. I think it's 49 satellites because of the effect that I was mentioning earlier. The fact that because of the solar activity, the thermosphere locally increased in density, and so at the launch, the satellites had exactly the right amount of fuel to reach their orbit, but because the drag they experienced was higher than expected, they consumed all the fuel and didn't reach the orbit, and then went back to Earth and burned in the atmosphere. So they actually lost, I think almost all the satellites, like 90% of the satellites for this specific launch. And they actually they knew that a solar storm was coming because we're working specifically on this forecast warning. But it was too late based on their schedule and everything, and they decided that if they lose some satellite, it was okay. I don't know if they regretted it because I know that they have some margin to to lose satellites, but this specific launch lost almost all his satellites. And we knew, I mean, we knew it. We knew it when working on space weather. We knew that the launch in the upcoming 2-3 days were an issue, and I think they just didn't care. So yeah, so I was mentioning the consequences. So there are a lot of consequences. So here I'll do like a worst case scenario, like what happens if a new Carrington event occur today. And so there are some disastrous consequences. The different category that I've put in here in the boxes are all categories that are impacted by space weather all the time, and the gravity of the impact is changing based on the coronal mass ejections. So for humans, mainly astronauts, but also humans that are in planes, like pilots, you experience a lot of radiations that are really not healthy. The GPS communications are really impacted too, and also the telecommunications. So because of the ionosphere gaining some charged particles, sometimes the very low frequency or low frequency of communications are really impacted. So it's actually very interesting and important. There is a model from the French army which is called FEDOM, which tries to predict the exact effect on communication and telecommunications based on space weather, because they have to know if for a given operation, a military operation, they will lose communications for a certain amount of time. Constellations are really at risk, debris too, because solar activity and all the particles can like remove a small amount of matter from some satellites by erosion, or things like this can also move. I was talking about the drag, so can also change the orbits of some debris, and so it's not really not helping on the collision avoidance. Oil drilling. So this is actually quite interesting. But when you drill oil, you use a magnetic. You use the magnetic field of the Earth to know where to drill and how to drill and how deep to drill, and in order to drill, you have to get to the place deep in Earth in one shot. You cannot really miss. You cannot really miss what you want to reach by drilling. So you have to be sure that your magnetic direction given back by the magnetic field of the Earth is the right one. And actually a lot of oil industries are investing a lot of money in predicting space weather, because they want to know when the magnetic field is not going to be reliable, in order to direct like the drilling. And yeah, we're talking about aviation and there also nuclear risk, and this is actually one of the biggest risks, because when a lot of particles are entering the inner magnetosphere and like the ionosphere, you can see it as a huge induction effect. Like you have a lot of charged particles in space around Earth, and so on Earth, on the surface, you have a lot of electrical currents that are occurring. So we call them geomagnetic inducted currents, and they tend to appear in all the electrical systems of nuclear central, and these geomagnetic currents actually they go back to the nuclear central, and they actually can melt the core of some of the power in the nuclear systems, and this is really, dangerous. So the nuclear industry is also checking a lot of space weather. I've written here, it's based on a few studies by Lloyd's, by the Swiss Academy of Sciences, and by a researcher. Maybe Patrick, I'll send you all the references that I'm using if it's of interest for the person that are looking at the slides. So this is just the worst case scenario. What if a new Carrington event appears? So they suppose there would be 20 to 40 million humans in risk areas. It would be several hundred to thousands of billions of dollars of loss. And it would be 4 to 10 years to repair everything. So the researcher Shibata actually tried to look at other stars that are quite close to what we have, so quite close to the sun, and try to look at the history of these stars in order to be able to understand, okay, what is the probability of having something that is 100 times more energetic than Carrington, or 1,000 times more energetic. And so these are his results that are debatable, but these could have devastating consequences, like the loss of all the electrical systems on Earth or something. So we have a lot of impacts. Actually, the OECD, which is the organization that is classifying the world risks, they now rank geomagnetic storms among the 5 global risks, like with the pandemic, for instance. Okay, so I stayed a bit longer on the risks and impacts because I think it's really interesting to understand how it is really important to study this and to make a link between operations, so all of these topics here, and theoretical physics behind space weather. So now I wanted to maybe quickly talk about what we do, and I mean, before jumping to AI, so how did we get to AI in space weather? So I was talking about it, but first we started counting the sunspots by barely looking at the sun. And in space meteorology, the number of sunspots is the most famous indicator of solar activity. But counting sunspots is not really, it's not as simple as it seems, since they can only be observed on the visible part of the sun and not behind the sun. So you don't really know how much sunspots you have on the sun at a given moment. And it's also actually quite different based on where from Earth you observe it. And finally, we have a lot of observation of sunspots. It actually started in at the end of the 19th century, but today the quality of instruments used for observations has really improved over time. So comparing the modern measurements and the old measurements is really challenging. We cannot really say that we see patterns when we know that our way of measuring really evolved and changed over time. So there are a lot of indices that we use in order to understand the impact of space weather. So we use global indices, and the first attempts to build these indices and to have these global indices was to measure the magnetic field. So measuring the magnetic field date back to the early 20th century, and it was a man named Julius Bartels, and he proposed an index called K, and it was in 1939. And this index is still widely used today. So it's now called the KP for planetary K. It's actually several measurements of K, which is basically a measurement of the magnetic field of the Earth on ground with magnetometer. And the association of all the measurements of magnetometers on Earth gives you, along with some mathematical calculations, gives you an index between 0 and 9 that we call KP. From this index, we built a lot of other index like AP and so on. But basically, it's an index from 0 to 9, 0 being quiet time and 9 being extremely dangerous, which is very rare. We had KP, but with the arrival of digital technology and the increase also in the number of observatories on Earth, other indices have been developed, and this includes, for instance, the DST. So the DST is also basically a measure of the magnetic field, but it looks at how the magnetic field is dropping when we have a geomagnetic storm. Without going into too much detail, when a lot of particles are entering the magnetosphere and are getting stuck in what we call the ring current, we have like a donut-shaped ring around the Earth that is getting a lot of charged particles, and these tend to attract the magnetic field lines of the Earth. So when you are on ground at the equator, you see a real depression and a real decreasing of the magnetic field, and the DST is actually measuring this. So this is for the geomagnetic indices. We also have AE, AU, but we have a lot of geomagnetic indices that are basically global to understand what is happening on Earth globally. We also have the solar indices. So I talked about the sunspots. The F10.7 is just a measurement of the radio flux at the solar flux at 10.7 centimeter wavelength. And it's a really, really good index. And one of the reasons is that we've been measuring it for a long time. So now we know that the F30, so the measurements of the solar flux at 30 centimeter wavelength is actually better, but we've been measuring it just recently. So for instance, for doing AI or statistical studies is not really interesting. So we keep measuring the F10.7, which is a very good indicator. So yeah, so that's just a glimpse also at some of the indices that we use. But overall, the magnetic and solar indices they do not reveal the underlying nature of the phenomena. They just are used to describe changes over time, but we require further analysis to fully understand the data and fully understand what's happening on a phenomenon point of view, on the theoretical physical point of view. But these are still widely used. And for instance, DST is used by NOAA. I was talking about SpaceX and the fact that we knew already that the solar storm was coming. The forecasts of KP and DST were really good at that moment, and we knew that something was coming. They are still widely used.
Okay, so if I try to think of a machine learning AI task, it would be for instance, an attempt to forecast these indices, so KP,
definitely, yeah.
DST. Okay.
So basically, what you're mentioning there is the very first attempt to use AI in space weather. It was forecasting KP or DST based on past measurement of KP or DST, and then this quickly improved to putting different inputs. So sometimes inputs from the sun. What we're trying to do now, and what we see in the literature is for instance using images of the sun. And so we combine sometimes AI, but I'll come back to it. We combine AI to, for instance, from an image, identify automatically a type of solar flare. So we do solar flare classification on an image. And then from this, we use this data to, for instance, forecast or predict what will happen on the geomagnetic indices on Earth. It's really easier to predict, to forecast KP and DST, for instance, than it is to forecast the proton flux, for instance, because the proton flux is usually local and also based on a lot of different effects inside the magnetosphere and not just when the sun is doing something. But the KP and DST really gives us how the magnetic field the shape is moving also. So the magnetic field is really moving a lot when you have a solar flare or coronal mass ejections. You can really see the compression in the front and the extension in the night side. So in this context, we have a lot of numerical approaches. We have a lot of physics-based model, and one of the ways where we use numerical approaches are in the transport of particles from the sun to the Earth. So everything that is related to plasma movements. And so usually we started with the first method, which is the particle in-cell approach, which describes the interactions of a small number of particles. And then we went to the kinetic approach, which is a statistical description of a large number of particles. So this is the Boltzmann equations, if you know them. And this gives a complete description of the plasma. And then the third and final method is the magnetohydrodynamics, so MHD approach. And so this one is basically describing the plasma as a magnetized fluid. So it's basically based on equations that are close to what we have in fluids and in movements of fluids, but we consider this fluid to be magnetized. So this changing a lot the properties and how it evolves and how it moves. But the MHD is quite sufficient for the description of non-collisional plasmas. So that's the case for instance, the solar wind. But this being said, we usually actually use hybrid approaches to combine fluid and kinetic descriptions of electrons and ion movements. So this is so we have theoretical equations that are quite horrible to solve and to simplify, but with some simplification, approximations, and so on, we can have cases where we solve these equations. For those of you who had a physics class, you know that you always try to find approximations or specific cases to reduce the complexity of your equations, and this is what we do when we try to solve for instance the Vlasov equations that are the equations for the magnetohydrodynamic. And so we also have, so this are what we call theory-based model. So it's just solving the equations that we know work in some context. And we have also examples of empirical models. So of course we have plenty of empirical models in all directions and in all fields, like in any fields of science. But I'm just mentioning here two examples, like the Tsiganenko series of magnetic field models. So these are based, for instance, on thousands of magnetic field measurements made by magnetometers on satellites. And it provides the three components of the magnetic field vector at any point in the magnetosphere. So it's really, really powerful and interesting. And of course, the IRI model, which is a very well-known model, it's a model for the ionosphere. So the ionosphere is the zone in our atmosphere where we have charged particles. And it's a model developed by international teams, and it provides the altitude profile of electron concentration for a given location and time in the ionosphere. So these empirical models are actually very, very interesting and powerful. And an example of a theory-based simulation. So it's not, it's a specific one that I've chosen here because it's one that I know and I'm working with a researcher from the University of Helsinki, and it's Vlasov. So Vlasov is basically a huge code that is trying to solve the Vlasov equation at any point in the magnetosphere. And in order to obtain one result, so one three-dimension representation of the magnetosphere, it's several days of running. So it's not, so it's really powerful, and they are trying to improve it, but it's not yet strong enough to give some real-time measurements and some real-time approach. So it's can I maybe change the slide? Yeah. So from these models that we have, so physics-based models, empirical models, we try to find an understanding on how space weather is related to, so how space weather is moving, so how magnetosphere moving, magnetic field are moving, and so on. But there are a lot of difficulties and a lot of limitations. So how did we get to AI? Well, first, the success of AI in other fields was a really good starting point for space weather scientists to start using AI in their field, and also the limitation that we have on our models. The physics-based models actually have not reached the expectations that we expect, the expectations that we had in predicting and modeling the space weather phenomena. And it's been around 20 years since we've been developing physics-based models to deliver a forecast and prediction. And it seems that we are not succeeding in having real improvements, and it is unlikely that we will do so in the future. And so the reason behind this is you have actually, it's just a quick remark. You have a really nice call by a talk by Enrico Camporeal on the subject. Maybe I'll send you the link, Patrick, too. And he's really expanding on this problematic. But the reason behind this is that we are unable to achieve the required level of accuracy in representing the physical processes in the Sun-Earth system. And this is due to the really high complexity, and it's also due to the lack of in-situ observations of space weather drivers. So it's actually a paradox, because we have a vast amounts of data, both real-time and in the past, but the data that we have do not cover the entire magnetosphere and the entire locations that we would like to see in order to understand on a physical point of view. But this vast amount of data is useful if we are talking in AI and if we are starting to do some AI. So the lack of observations is actually a lack of observations to be assimilated in numerical weather prediction. And this makes it difficult to initialize and assimilate the data into these models. And finally, I've been mentioning it, but the arriving of the new space actors actually urged the need to obtain short, mid, and long-term predictions for operators, but also for insurers. And we've been talking actually with my the startup. I mean, we've been talking with insurers, and there is a real need to understand how this will evolve in the mid and long term, and this is really not done yet. Today we have some good predictions to a few days or sometimes few hours, but we have no idea if we will have this amount of geomagnetic storm on this day in a year from now. We doubt that it is possible, but yet there is no specific studies on this. So a lot of things have started in AI apply to space weather. There are a lot of H2020. So it's Horizon 2020. It's a huge. I don't know if you know it, but it's a huge programs that receive a lot of finance and combine a lot of different researchers in order to answer one problematic. It's a European financial project, and a lot of the Horizon 2020 recent Horizon 2020 are space weather oriented and forecast and prediction of space weather, which is really a good thing. So this is actually taken from the talk from Enrico Camporeal that I was talking about, but this is just to give a quick view on how and why AI quickly made its way to space weather because of the advantages of using machine learning and artificial intelligence. So for instance, here it's the table here compares the different pros and cons of each method. The first three methods here are basically physics-based or empirical-based models, and we see that the machine learning one actually has a lead time which is as good as the best physics-based model, but has also a built-in uncertainty quantification, which is really useful. And finally, and this is, I think, why everyone is asking for AI in space weather, it's really less expensive and more efficient in providing a result. So this is these are mainly the reasons why space weather is now experiencing a lot of AI, and so there are a really, really large amount of topics where we can apply AI to space weather. We were talking about forecasting the geomagnetic and solar indices, but we can actually do a lot of things like the coronal hole. I was talking about it, the segmentation of coronal hole, the classification of solar wind. Just for your information, the solar wind is usually classified in slow, fast, and explosive. So we have different type of solar wind, and it's sometimes really difficult to classify. And we have a lot of data in the past, so it's really nice to have an automatic classification of solar wind. And the classification of solar flares also by looking at pictures of the sun or forecasting solar flares. For instance, deep flare here is a tool that is used to forecast to classify solar flares. But we can also have forecasting of electron, proton, GCR, galactic cosmic rays, fluxes at different orbits, satellite anomaly detection, ionospheric scintillation forecasting. So this is the fact that the GPS is really impacted by the charge and discharge of the ionosphere in particles. And we have here an example of a recent Gaussian process neural network that was done in 2018. In predicting, so this is the DST, in predicting the DST 5 hours ahead. And we have, so the observed DST here, which is going really down, minus 400 is one of the highest geomagnetic storm that we can have. And so the prediction with the Gaussian process is actually way better than the prediction made by the Space Weather Prediction Center, which is NOAA's prediction center for space weather. And it's a 5 hour ahead prediction, which is also really good, a bit better than what we do actually. And we can see that on this particular case, which is a DST going really low, it's very, very difficult to have accurate predictions on these ones because they are really rare events. So it's very difficult to train algorithms on these events because we have maybe 5 to 10 of these events in the past 20 years. So it's difficult to train AI on it. But this is so to give you an overview of the amount of subject that we can cover with AI applied to space weather. And actually, if you're interested in this topic, we can watch the presentation by Enrico Camporeal. He's really diving into the challenges of each of these categories of machine learning in space weather. But on my side, I'll just try to talk about my PhD thesis in this context. So in my PhD thesis, I'm trying to predict the low energy particle fluxes, and actually I'm trying to predict the electron fluxes in low Earth orbit. So actually, what I'm predicting are what we call the precipitated electrons, and these are the electrons that are causing the auroras mainly in both poles. So for this, I'm using a satellite, a family of satellite called DMSP, but I'll come back to it, that are going over the poles, and so they are able to make the measurements that I want, the measurements that are my output measurements. So the DMSP measurements for me are my ground truth, and I'm using them to train my algorithms. And my inputs are measurements from the interplanetary magnetic field and medium. So mainly speed, temperature, density, and X, Y, and Z component of the magnetic field of the solar wind. So as measured by the satellites that are outside of the magnetosphere. And the overall point is to have something that is able to predict what will happen really close to Earth based on something that is happening out of the magnetosphere. And this is to like bypass all the complex phenomenon that are happening in the magnetosphere. But it's Of course, I was saying that there are also a lot of things that are happening in the magnetosphere independently of the sun, and this is so this is not taking it into account. But I'm also adding a few tricks in order to have this phenomenon.
And Simon, for this low energy electrons, so you mentioned they are causing auroras. Do they have also adverse effect on or in one of these components you mentioned earlier?
So you mean if they have some negative, like
Yeah.
danger effect? Yeah. So basically, on the different effects that I was mentioning, one of the main effects from these electrons are the surface charging. So these are electrons that are accumulating on the surface of satellites in LEO, and triggering electrostatic discharges on the surface of satellites. And actually, my PhD is really linked to what I'm working at my startup, and at my startup I'm working with colleagues on the effects and the different effects on satellites. And so basically what I'm studying here is a good starting point to understand the surface charging and this risk on satellites in low Earth orbit. And
makes sense.
one of the interesting aspect of it is also the fact that most of the future constellations in the upcoming years will be in low Earth orbit, and the low Earth orbit is actually an orbit that we don't really, I mean, we have studied a lot the low Earth orbit, but not as much as we studied the geostationary orbit. So yeah, so satellites of the upcoming constellations will be at risk, and this is why I'm working on this topic. And so so of course I've tried a lot of things, classic neural networks, LSTMs, but the final architecture that I'm using is a TCN, so a temporal convolutional network. And so a TCN is stands for temporal convolution network, and it's a type of neural network architecture. So there are a lot of different TCN, and it's basically a convolutional neural network, but in time and in 2 dimension instead of doing it in 3 dimension. So TCNs are using convolutional layers to extract the features. So it's really well suited for processing sequential data, so time series data, and they are really similar to the traditional convolutional neural network, because they use convolutional layers to extract the features in time. But unlike the convolutional neural networks, they are designed and optimized for processing temporal data instead of spatial data. So they actually arrived in 2018 with the paper that I mentioned here below, and for the different trials that have been made, they constantly perform better than LSTM or GRU architecture on a lot of tasks, and mainly on temporal and time series data. So I wanted to try this, and so I've stated here the different advantages and disadvantages of using TCN. But one of the advantages of using TCN in space weather applications is the fact that they can handle unevenly spaced time series data, and they can model long-range temporal dependencies. But yeah, one of the main disadvantages of it is that they suffer from long sequences and they require a lot of training data. So what I'm doing here, just a small note on it. It's a causal neural network. So that means that the value that I'm about to predict, and hope it's good news, but the value that I'm going to predict is only based on the the past values of my time series. And one of the biggest difficulties that I had is the fact that if I miss one data in my time series, in my input time series, I cannot do any prediction. So, and it's very difficult in space weather, I guess, but in physics in general, I think, to make some data augmentation or to do some interpolation to fill in missing values, because the data have a lot of noise and we barely know the signal to noise ratio, and sometimes we have large amount of missing data, and on top of this, when we have very high values, eruptive values from the solar activity, instruments are awfully saturated and do not perform any measurements. So sometimes missing measurements means very high values, so we cannot just interpolate the values.
Yes, that's a very good example of when the lack of information or the lack of data is actually, or potentially, an information as is, and we cannot really be sure what to do with that. So yeah, that's a very good example of it.
That's true. In fact, I've spent a lot of time analyzing the size of the gap of data inside my data. Like if I have, for instance, when I have perfectly, how to say this, when I have exactly, because I have one measurement per second or per minute, when the amount of missing data is exactly 1 week, this means that we are performing some intervention on the satellite. So something like an update on the software or something, but someone on Earth is using the satellite for something else for all week, and it's not really because at this moment the solar activity is high, and so we had to perform actually like tricky analysis on statistics of missing data in order to maybe identify missing data that means something, missing data that are just missing data, and the ones that means, for instance, high solar activity.
And based on all of this data pre-processing work, most of our work is a lot with the data preparation, cleaning, and so on. So this fits well. I'm curious to know, this data, are they publicly available data?
Yeah.
Or do you have like specific partnerships for you?
No, most of the space weather data are actually publicly available. Okay. I think it's because I mean it's not a field that is yet very commercial. So for now, everybody favors the sharing and the publicly availability of data in order to have a lot of researcher working on different topics. So yeah, so basically the data that I was mentioning are publicly available, although the DMSP data of DMSP is the Defense Meteorological Satellite Program from I think it's the American Air Force, I think, but they changed an instrument, I think, in the last few years, and we missed data starting 2021, but it's still almost 25 years of data, consecutive data, and one measure per second on 25 years is a lot of data. So we have a lot of things that we can measure. So I was mentioning it. Basically, this is in my input output in my architecture and in my subject. We were talking about dealing with missing data and preparing the data. Well, preparing the data has been maybe 2 years of my 3 years PhD, and only a few months on building the architecture and trying to use the neural networks. So basically what I've been doing, at first I was taking data from a satellite called ACE, for Advanced Composition Explorer, a satellite that is in between Earth and the Sun on the Lagrange 1 point. But we have way too much missing data in that satellite, and so we switched to the bow-shock nose. So the bow-shock nose is really the point here in front of the Earth magnetosphere, and there is the Omni dataset. So the Omni dataset is a dataset built by NASA, which is taking in a lot of satellites in entry as input, and is then combining them and propagating the information to the bow-shock nose. And so what I'm taking is the Omni dataset at the bow-shock nose. There are a lot of issues with the way they propagate the data, and it's really debatable, and the data are not perfect because they are not in-situ data, but pre-processed data. But still, it's a good data set. We have a lot of data, and it's the easiest way of getting data that are relevant for this study. But this reduced by a lot the delay between my input and my output, because my input was the satellite ACE in the middle of the interplanetary medium, and now I'm really right at the bow-shock nose. So now it's a few minutes between my input and output, which is a bit disappointing, because one of the key behind nowcasting the electron total energy flux was to have a forecasting just by the fact that we have the data before the particles are arriving. Now we still have a forecast for a few minutes, but it's not as much as it was when we had the ACE satellite. But well, this is a lot of improvements path that we might tackle in the future. How to use ACE, still use ACE, or maybe how to use data from the sun or images from the sun to improve the algorithm. And in the output are the DMSP family of satellites. So I've just made this small table in order to show the availability of data. So there are actually a lot of years when we have 3 or more satellites at the same time. And all satellites are making measurements every second. So we have actually a lot of data. And we are combining the North Hemisphere and the South Hemisphere because we want to have as much data as we can on a polar view. By doing this, we actually remove some effects that are asymmetric between North and South poles, mainly caused by the X and Y components of the solar wind magnetic field. But this has been taken into account in our algorithm, and in the output we want to maybe split between North and South, but in this first version this was the easiest way of doing it, in order to have the large patterns from the input. And so in my input I take 30 minutes of data, so 30 consecutive minutes per feature. So it's actually a lot of inputs, but the TCN is doing a parallel measurement, parallel computations with the filter it uses. So we gain time compared to a classic neural network. And so this, so I cannot really show you the results, actually, because we first hope to publish it, and second, some of my results are also going to the startup that I'm working with, because it's a joint work between my university and the startup. But here is an example of what I'm doing mainly. On the left side, you have Ovation Prime, which is the main model that is used actually today to model the auroras, so the electrons that are precipitating. And on the right side is just one output of my algorithm for a specific date and time. It's not a chosen date and time. It's just a random one. So this is the output of my algorithm, based on, this was difficult, but it's based on measurements of satellites that are, of course, path of the satellites above the pole. So we had this difficulty of taking care of the measurements of the MSP that are at a specific point and at a specific time during their orbits, and the fact that the output that we really want is a polar map at a given time. So this also implies, for instance, computations and interpolations of data that are close in the spatial distribution of polar maps. This plus the fact that we, of course, needed a lot of data at a lot of different points. But we have some nice results. I can maybe show you this example. So DMSP is the green line. Just for the information, Ovation Prime is also based on DMSP. So it's also a model that is using DMSP to predict the auroras. So here I have a result that is better than the Ovation Prime for now, because Ovation Prime is overestimating a bit. This is actually known in the community that Ovation Prime is overestimating. But we still have a lot of improvements to do. Of course, here I'm showing something that is pretty much good results, that is working well, but we have examples where it's not working that well. So I'm still working on it, and this will maybe be a paper in the upcoming month. So you might see it coming in the upcoming month. But that's it. That's it for the small introduction to my work and what I've been doing for my PhD. I was very long. I'm very sorry.
It's fine. It's fine.
An hour and a half. We might have lost some people along the way, but yeah. But
not much actually. I think a lot of people are still there from the beginning. So you must have been really clear and not much questioning yet. So I think it's good. Thank you very much, Simon.
Thank you, Patrick. It was quite interesting to prepare this. I've never tried to present the whole thing from space weather to AI, applying AI, and also a bit of my research. So it was quite challenging for me, but really nice, and I'm very glad I could do it.
Good. I hope this also helps you a little in the preparation of your defense. I guess you will go a bit more into the nitty-gritty details.
Yeah. I will barely present space weather, I think, but I think I'll spend some time talking about AI, maybe even more than here, because I actually considered that here the public was more of an AI public, while for my defense would be an astrophysics public mainly.
Right.
I mean, I think I'll have like one member of my jury who will be AI oriented, but most of the people that I'm working with are in astrophysics, so I'll spend some time explaining AI, which is nice too.
Nice. Well, thank you. So I think I will still make a call for questions if people have some specific questions about what you presented, or maybe in general. Maybe I would ask one to you, Simon. Is if somebody is interested to get into or to play a little bit with some of the space weather data. Sometimes we have also students who join or watch the replays of such presentation. Where would you advise them to start with if they would like to? Well, I guess first your presentation is a very good introduction, but if they want, for instance, to get some data.
Well, there is actually a nice. I can maybe find the link and put it in the chat. There is a challenge. So I think those of you who do artificial intelligence know, for instance, websites like Kaggle, websites of challenges, and so I think in December 2020, well, maybe 2 years ago, there was a challenge of predicting the DST, so geomagnetic index,
Oh, yes.
based on data from the solar wind. So this is basically the things that I've presented here. This encapsulate all these things, but it also prevents you from doing too much data preparation, because it's a challenge. So the data are already there. So if you want to dive into the AI but apply it to space weather, it's actually a nice challenge to tackle. I can send the link here.
Yeah, I'm trying to find it again. Oh, good. Yeah, it. Thanks.
So yeah, so it's actually very nice, well done challenge. They explain what DST is. They explain a lot of things about the magnetosphere. They give the data and explain what the data are. So it's really, yeah, it's really nice it's basically to do AI but do it in space weather. It's really nice.
Okay, I see. Okay, so Simon, I think it's time to wrap it up. I don't want to hold you too much from your evening schedule.
All right.
Thanks for your presentation. I wish you all the best for the remaining months until
Well, thank you,
your PhD
Patrick,
descent.
and thank you everyone for attending it. It was really nice to do, and I hope that some of you will start watching space weather and space weather alerts.
Yeah,
and
definitely.
everything. There is a nice website called Space Weather Live, if you're interested, and it's basically like a meteorology website, saying, like, sending alerts on geomagnetic storms, solar flares, and everything in real time. And it's pretty well done.
Do they have APIs for us to get to get alert and maybe integrate it into our
Well, they
applications?
have a nice app, like on Android and phone app. So you receive the alerts and everything. I don't know if they have I don't know how the API is and if it's a good one, but you have a lot of indices on it. You have a lot of explanations, a lot of pedagogy links and everything, and but it's not based on what I said during the presentation. It's not tailored for operators that want to know what they risk. So basically, if you download this app and put it on your phone, you will know if a geomagnetic storm is coming, but you cannot really do anything about it, and you don't really know what you are risking with this specific geomagnetic storm. But that's basically the work of the startup that I'm in. So there are room for improvement in
so
this.
if people wants to get better prediction, they have to reach out to you.
Basically.
All right. Thank you, Simon.
Thanks
you
a
for
lot,
people
Patrick.
who have joined, and
Thanks, everyone.
I wish you everyone a good rest of the day. And we have people also saying thank you in the chat. So
well, thank you,
great
thank you,
job.
everyone.
Bye bye.